Hello, everybody. My name is Matthew Alt, and I'm going to be teaching you the HackadayU course, Introduction to Software Reverse Engineering using Ghidra. So let me get this chat out of the way. So I am a reverse engineer with a focus on embedded systems. Currently, I work for Caesar Creek Software as a security researcher, but I also provide training and assessments through a company called VoidStar Security. Some of you may also be familiar with some of my work through that's been presented on Hackaday before under the username WrongBot, where I tear down various embedded platforms and use those as a mechanism to teach various hardware reverse engineering concepts. So without further ado, let's jump into what we're going to learn today. So today we're going to talk about what software reverse engineering is. And in order to do that, we need to understand how software is engineered in the first place. So what we're going to do is kind of start with an initial run through of how you go from C code or some high level language to something that actually runs on your processor. And then after that, we're going to jump into software reverse engineering 101. So taking a look at how can we pull information out of these programs and how can we glean information from these compiled programs and kind of start working backwards. And that's where we're going to get into Ghidra. We're going to talk about how to install it and then how to use it with a couple of exercises that we'll work through together. And then finally at the end, we'll take some questions and kind of walk through everything that we learned throughout today. So, the big question here, what is software reverse engineering, right? This is the process of analyzing some software system for which you don't have the source code for. So maybe that's a firmware blob, maybe it's some shared object or an executable. Let's say perhaps you want to figure out how some proprietary binary blob works that was distributed with a microcontroller that you got, or maybe some game drops a DLL to your system when you play online and you want to know exactly what that thing is doing. So in order to do that, we kind of have to break down software to its fundamental core components. So we have to go down to the lowest layer of abstraction because that's all we know as a ground truth when we're reverse engineering something. And what that is machine code, right? So most of us are probably familiar with the concepts of, machine code and assembly language, and we're going to go over that throughout today just so we know that everybody's on the same page. But what we wanted to kind of clear up with this slide is, software reverse engineering is kind of the process of taking a compiled piece of code and working backwards from that to figure out maybe what that code does by starting at the lowest layer of abstraction, the lowest level of abstraction, the machine code. And so in order to understand how to kind of work backwards from this stuff, we need to know how it's engineered and how it's built moving forwards. And so most of you that have written code, whether it be for, a microcontroller or a desktop operating system, et cetera, that code is written in some high level language, C, C++, JavaScript, some maybe even a scripting language like that. That code is eventually compiled and interpreted into machine code, which are sequences of bytes that the CPU then interprets in terms to perform various abstract arithmetic operations. And so disassembly is the process of taking those byte sequences and reconstructing assembly level instructions from there. And if those terms are, unfamiliar to you and you're not super familiar with what they mean, we're going to go over that today. But the core point here is that as reverse engineers, that final product, that compiled bytecode that's going to run on the CPU is going to be our starting point. So that's where we're going to start. But again, in order to figure out how to work backwards, we need to understand how we got to that point to begin with. So we're going to do a brief review of what happens when you compile code or you run code. And quick disclaimer here, I am not an expert in compiler theory. This is kind of a high level overview of how code goes from a human readable language that you and I can understand to a sequence of bytes that run on your CPU that we're going to learn how to understand. And so compilation is kind of a multi-stage process. So we're going, like we said, from source code to a sequence of bytes that are going to run on the CPU. And that involves 4 steps: pre-processing, compilation, which is slightly confusing because it's under the umbrella of compiling a program, and then assembly and linking. And again, the result is a file that will be run on your CPU. I'm going to check this chat real quick to make sure everything's okay. All right, looks good. And so typically when you write code, if any of you have written code for, an Arduino, or maybe you've written something using code blocks, a lot of these steps are performed automatically for you. So you don't really get a deep look into how this works. Now, some of you that work in the embedded space are going to be familiar with this because you kind of have to be in order to get code to run on some of the more esoteric platforms. But we're going to go through this process from kind of a high level so that everybody understands what happens when we take C code and compile it to something that'll run on, our modern computer. And again, really want to highlight the disclaimer here that each of these fields are, extremely complex fields with, multiple research areas, et cetera. This is just going to be a high level overview for all of us so that we know we're all kind of from the same starting point. So we talked about how compiling is phase 2 of compilation. Phase 1 is kind of the pre-processing. So if you've written code before, you're familiar with the idea of, adding comments and maybe macros and things like that. When you put include headers at the top of your code, these are all things that are interpreted and then processed during this pre-processing phase, because the comment that you put in the code is not going to actually be run by your processor or interpreted by your processor in any way. So the pre-processing phase gets rid of all that stuff and expands any macros that you might write and kind of gets rid of that extra fluff that we don't need. And what actually happens during, phase 2, when we compile it, we take the output of that preprocessor, that C code that you've written, and that then gets converted into assembly code. So here's a simple example of what happens when you take, the classic hello world example and compile it. So this is just assembly code. This hasn't been converted to anything that can run on the processor, et cetera. You can run GCC with a certain flag to only produce the assembly code. And this is just a small segment of the assembly code that's present for Hello World. But what I wanted to illustrate here is that the first stage in taking that C code to something that can actually be run on your processor involves interpreting it and then turning it into this assembly code, which is still, technically human readable, but you wouldn't necessarily want to be writing in this all the time, which is why we have the C compiler, or any other compiler for that matter. So after that, we go into the assembly phase. And so what that does is it takes these instructions that we have here, so these machine level instructions, these low level instructions, and these instructions get converted into hexadecimal or binary opcodes that are actually going to be interpreted and run by the CPU. So when we talk about machine code, this is what we're talking about. And so, for example, what happens during this phase is you take something like the move instruction, which, if these look unfamiliar to you, we're going to cover them in a second. This is just to sort of outline how the end-to-end process works when you write software, build a program, for those that might not be familiar. So we take this move instruction, and that gets converted into this number sequence, essentially, this binary opcode that is actually interpreted and run by your CPU hardware eventually. And so the output of the assembler is an object file. This object file has opcodes in it. And so again, what these are the binary representation of what actually gets interpreted and processed by your CPU. And so I know most of you are probably familiar with the concept of assembly language. Maybe you've never written in it before, but this is an example of what happens when you assemble this to something that can, again, actually be interpreted by your computer. And as reverse engineers, this is going to be our starting point. So we have to use tools like Ghidra and others to work backwards from, these binary sequences to the assembly code. And then eventually we can even go back to C code, and we'll show how Ghidra enables us to do that later. But we're not quite done with the process of building code. So we've taken that C code, we've ripped out all the comments, we've expanded the macros, anything else like that. We've generated the assembly code from that. From there, we generate the byte sequence with the assembler, or the byte code, the machine code here. But there's still lots of things that the operating system needs to know, right? So these are just instructions that the CPU will certainly run, but the operating system needs to know things like, where do I put this in memory, and what other libraries are needed? What does the runtime look like, etc. So all this information is added during linking, because again, this object code is almost there. We're 3/4 of the way there, but the operating system needs to know, where do I load this in virtual memory? What are, the various memory permissions, things like that. And so this is what linking does. And if you've worked in the embedded system space before, you've probably written linker scripts to define things like, this chunk of memory is for SRAM, and this chunk of memory is going to be for the stack or the heap, etc. And so the linking phase adds all that information into the object file so that it can finally be run by the computer. And so what that might look like is we have the output of objdump here. And so if you notice on the left, we have all these fields like the text section, the data section, BSS. These all might be, alien terms to you. You might not be sure what these mean yet, and we're going to go over that. But what happens after linking is these fields get filled out with actual addresses so that the operating system knows where to put these things in memory before they get run. And so in that .text section, you have the raw machine code. In the data section, you have any kind of variables that you might need while it's running, etc. And so linking basically fills in the needed information by the OS to run this program. And there's also linking is also used when you're compiling against another piece of code, etc. But for right now, what we need to understand is that linking fills in the necessary fields and information that the operating system needs to run a program. And so what happens after things have been linked is you finally have, an executable output format. And so on Windows, that's, a PE or a .exe file that you're all familiar with. On Linux, that's an ELF file, which is what we're going to be focusing on. And on OS X, it's a Mach-O. And then some of you, again, maybe from the embedded space, after you build something, you either have maybe a .hex file, or maybe it's an ELF file that you'll then load onto an FPGA or something like that. But the key point that I wanted to make here is that this output file, after the result of everything we just talked about, is going to be your starting point as a reverse engineer. You don't have source code. You don't have anything else like that. And so for this course, we're going to focus on the ELF format. And so we're going to talk a little bit about how the ELF files are formatted here. So ELF stands for executable linking format. And again, it contains information identifying, what operating system it's supposed to run on, the endianness of the data, things like that. And so ELFs provide lots of information, whether they're being used for, linking or actually running. And what we need to know for the purposes of this course is that in the ELF file, in that header, it provides all the information that's needed for the operating system to load and run that program. And we can kind of break the ELF files up into three components. We have the header that sort of defines the program, and then sections and segments. And so the reason we want to go over this is that this is a kind of a treasure trove of information for you as a reverse engineer, because this format is standardized. You can use it to kind of figure out different things about binaries, and we'll show later on today how Ghidra can take the fields from the ELF file and use it to aid us in RE. And another thing about ELF files as reverse engineer that you're going to find extremely useful are debug symbols. So again, those of you that have written code in something, like code blocks or etc., you can set watch points on certain variables. You can, set breakpoints on specific function names. This is possible because the ELF file basically presents this information to the operating system or to whoever's running it and says, hey, this function is going to be at this location and this variable is going to be at this location. And so you can imagine if you're trying to figure out what code is doing, having symbols contained within there is extremely useful because you might be able to figure out what a function's name is. You might be able to figure out um, things like that, which if you're looking at a function and you're not sure what it does, but then you can find out from the symbol that function is called, check password or something like that. That's extremely useful for you as a reverse engineer. And so to kind of close out ELF files, the ELF file is used to tell or inform the OS how to lay out a process in memory or how to set up everything such that that machine code that we generated from the C code can actually be run and processed by your CPU. And so there are lots of tools to kind of read and analyze ELF files, and some of them are listed here. We also have a couple of exercises about ELF files in the Git repo that we're going to talk about during the office hours. And so the point of this was just to give an overview of the output file that you're going to be working with in this class and kind of how you get to that output file starting from C code. And, because we're all going to be low level people after this course, we have a kind of a pixelated view here of what the compilation process looks like, right? So just to kind of recap what we talked about, and again, this was a 10,000 foot view of compilation and assembly and linking. I do not claim to be an expert in any of these fields. This is just an overview for everybody so that we can all be on the same page. So we go from our C code, we compile that, and then we have assembly code that gets generated. And so that assembly code is then assembled into a sequence of bytes. But that sequence of bytes needs more context to actually properly be interpreted by the CPU and run by the operating system. So that's where linking comes into play. So after we link it, we're left with an ELF file. And I know Link's not an ELF. He's, I forget exactly what he is, like a Kokiri or something, but I think the point is made here. And so with that, just to kind of close out this first initial session, why are we going over this? Why do we care about this? We're reverse engineers. Well, when you're reverse engineering, be it software or hardware, information is extremely limited. You don't have source code. You might not even have something like an ELF file as you get into more advanced targets, right? So you need to have some understanding of these fundamentals so that you can step backwards from this and then eventually get to that machine code and then get to the assembly code that you care about or that we're trying to figure out. And so the main reason that we go over all of this is just that so that from your starting point where to go when you're handed a file for this course and you have to work backwards to figure out what it does. And as we said, this resulting ELF file from the compilation process has that machine code embedded in it, and the ELF headers and fields can be used to pull that out. And from those bytes, we can actually work backwards into create an assembly language representation. And that process is, as you might have guessed, called disassembly. So what I'd like to do here is, I see there's a couple questions in the Q&A. So I want to take a quick pause right here now that we've gone through, your 19-minute introduction to software engineering, and make sure that there aren't any huge questions here. So let's look at the Q&A. So, okay, so we got two good questions. One from Michael Mai says, when is code obfuscation executed? And that can happen at a variety of phases depending on the type of obfuscation that's being added. And so I know that's not a perfect answer, but there are things that will manipulate, the jump instruction so that it might not jump to where you think it's going to jump and things like that. So obfuscation can kind of happen at multiple points in the compilation process, depending on the method of obfuscation used. And for those of you that don't know what obfuscation is when you try to manipulate the result of compilation so that it's harder for people like us to come in and figure out what it's doing. And then Dave asks what we would consider .NET stuff. So .NET is kind of a runtime that everything exists in. It's certainly not my area of expertise necessarily, but essentially that stuff still gets broken down into a sequence of instructions that run on your CPU. And that, at some point in the process, regardless of how high the abstraction layer is, it does get down to that point. Now, if you're reversing .NET, does it make sense to immediately throw it into a disassembler? No, there's things like .NET reflectors that can be used to decompile, or decompile is probably the right word, .NET code. Okay, and then I have another question. Oh yeah, we are definitely going to post the slides after the class. What I'd like to do is probably clean them up and take some notes out and things like that, but I'll post them on the project page after the class. And so I'll take one more question here. We have, do people obfuscate by handwriting assembly, or are there obfuscating compilers? So you can do it, again, you can kind of do it in either way. There are tools to obfuscate, and I believe that there are tools that exist. You can try to kind of obfuscate at different stages of the compilation process. So it depends really on what you're trying to protect against necessarily. So yeah, there are tools that can do it. It would be kind of difficult to do it by hand on a modern machine, I would say, but that certainly doesn't mean, people do it. Okay, one more question. How often is obfuscation in play? Great question. It really depends on your target and kind of what they care about. So, you'll see it for, essentially things people are trying to protect. So yeah, it's, how often is kind of a tough question to answer. I would say it depends on kind of the research area that you're working in, right? So if you're looking at lots of bare metal firmware that has limited code space, they don't really have the resources to, obfuscate and deobfuscate necessarily. But, if you're looking at a game, or you're looking at some other platform, like a more modern platform like that, there's a good chance you'll see it. And okay, so Harry is asking how to identify, packed or encrypted data using Ghidra. We will get into that at a later, kind of in a later session. And we can also, we can discuss that on the course page if you want as well. And then, okay, so this is going to be the last question for this section. Mike T asks, any binary can be reversed? I mean, technically, yes, right? So if, depending on, like we had the question earlier about .NET and things like that. So depending on the format of the binary, yes, eventually it can be reversed. Now, the steps that you might have to take to get it to a point where you can actually understand it are going to vary based on whatever the target is. And that's why for this course, we're focusing on, ELF files. Okay, Mikey's lab, do you have resources for extracting binaries from a platform or microcontroller? Yeah, actually, so if you look at my website, I do that fairly regularly on a handful of different platforms. So grabbing things over JTAG, SpyFlash, etc. And that's at wrongbod.github.io. And that might be a good starting point if you're looking to do that. So all that being said, what I'd like to do is move on to kind of the next step. So we've gone over how, programs go from high-level C code to something that we can understand. Let's talk about now how that's interpreted and what that might look like. So, computer architecture 101. Again, this is probably something a lot of you are familiar with, but for those of you that aren't, it's important to kind of understand from a high level. When a C program is running, or any program is running, there's a sequence of events that have to happen. So the instruction gets read into memory. That instruction is then processed by the control unit, or the ALU, and then the result of that instruction or operation is stored into memory or registers. And if some of those terms maybe don't make sense to you, we're going to kind of go through all those right now. And so for this course, we're going to be looking at predominantly C programs. And from a high level, again, we can sort of break these programs down into 4 core components. So we can think of them in terms of, registers, instructions, stack memory, and heap memory. And we're not going to cover heap memory today. We're going to get into that in the next section. So for today, we're going to cover registers, instructions, and what the stack is. And so This is, kind of a nice picture of what is actually happening while your computer is, running and doing things. So you've got this multi-step process where you fetch an instruction from memory, run it, and then store the results. And so, this is again a extremely high level view of how that stuff works. But to kind of dig down a little deeper, what we're going to have to do is reverse engineers, right? We're going backwards from, machine code. We're going to focus on x86 64-bit. So x86 64, as the name implies, is Intel's x86 64-bit version of the x86 architecture. It contains multiple modes for, back compat with 32-bit binaries, etc. The spec was originally created by AMD in 2000, and the reason we're, picking this for a starting point is because it's commonly used in, desktop and laptop computers. And so we talked about, breaking down programs into what we're going to call today just 3 core components: stack, registers, instructions. Let's talk about, what registers are. So registers are small, you can think of them as small storage areas used by the processor. You can even sort of think of them as, variables in a sense when we're looking at assembly language, but that's probably not the best way to think of it. x86 64 has 16 64-bit general purpose registers that you'll see used, in assembly language. And these registers in assembly are typically represented with different mnemonics here based on their size. And they can be operated on differently, based on this, the way that they're represented here. And so R0 through R7 have particular names that we kind of cover here in this table, and we'll get into what these names mean and what they stand for later on in the course. And then R8 through 15, for the purposes of this course, don't have any particular name. They're just used when extra space is used, or needed rather. But we've also got some special purpose registers like RIP, the instruction pointer. And as the name implies, this points to the next instruction to be executed, and it's 64 bits wide. You also have the R flags register, and what this is used for is kind of storing the results of different conditional flags that are set during arithmetic operations, and we'll talk about what that means later and all the implications within that. You also have, floating point status and control registers. We probably won't get into those in this lesson, but maybe in 3 and 4 we might talk about those. And then most importantly, we have RBP and RSP, which is for stack manipulation and usage. And I know we're throwing the term stack around a lot, and if anyone here doesn't know what that means, we're going to get into that later. So this is just to kind of highlight the different registers that x86 64 uses and that we'll be focusing on for the first few exercises in this course. So we have registers. These are kind of like our variables, our storage buckets for data as we, run instructions on the CPU. But what am I talking about when I talk about an instruction? So an instruction, at an extremely high level, defines a particular operation that's being performed by the CPU. And so that might be, addition, subtraction, multiplication, etc. Because even though, when we look at a modern computer and there's all kinds of stuff going on, all of that eventually gets boiled down into, what are essentially arithmetic instructions that are being run by your CPU. And that's that lowest level of abstraction that we're starting with. And so that's why it's kind of important to cover this stuff. Instructions can have multiple operands. There's a ton of them for x86 64. When you're reverse engineering something like this, you typically want to have those manuals kind of ready to go so you can look things up. But what I wanted to do to kind of get everybody up to speed again and sort of on the same page is go over some of the commonly used instructions for x86 64. The first one we're going to talk about is the move instruction. And if you could guess by the name, what this instruction does is it moves data from one register to another, or a memory location to a register. So again, if registers are these fields that we use to store data in, move can swap the data around or move data from one register to another, or a memory location to another. So the 2 examples we have here we have the instruction move RAX RBX. And what that does, takes the value in RBX and stores it in RAX. And then next we have move RAX RCX, but you'll notice RCX is in brackets. And we'll talk about this later on today, but what that means, what those brackets mean, is that that is a different type of addressing mode. And essentially what that means is instead of the value in RCX, we're going to take the value pointed to by the value in RCX. And so when I say pointed to, what I mean is, let's say RCX has the value hex 10,000 in it. Instead of storing hex 10,000 into RAX, we're going to store what is at address hex 10,000 into RAX. And so this is, the move instruction. And our examples here have RAX and RBX. This could be any of those general purpose registers that we talked about, right? So after that, let's talk about, kind of the next building block here, adding and subtracting, right? So we talked about how a modern CPU is still just fundamentally running, various arithmetic operations at a low level. So add and subtract is one of those ones that it can do. And so what the add instruction does is it adds the two values together and then stores the result in the first argument. So for example, add RAX RBX, we add RBX we add the value of RBX to the value in RAX, and then we store that result back into RAX. And those of you that are familiar with C or have written some code before, this kind of pseudo code here represents what this does. And as you might have guessed, subtract works in a very similar way, except for we subtract the value in the second operand from the first one, and we store the result in the first operand. So these are two more, arithmetic instructions that can be run and that you'll see. And so the purpose of this course, and like what we're going to learn how to do and what Ghidra is going to help us do, is go from these arithmetic instructions that might at surface level seem, very abstract and very, kind of non-informative, to we're going to be able to take these and turn them into, high level C code operations. And then, eventually we'll take that even farther into saying like, oh, I think this program based on these instructions is reading data from here, doing this operation on it, and then returning. And so that's why we're going over these things at a low level, because we're going to learn how to work backwards from this to give it, kind of a bigger meaning than just the arithmetic that we're looking at. And so, in addition to these, more common arithmetic instructions, you have, of course, binary operations that can occur. So those of you that are familiar with digital logic are, going to be familiar with some of these operations, and, or, et cetera. And they work in a very similar way to, add and subtract. So and RAX ands those two values together and stores it back into RAX. And, as you can imagine, this does very little, right? Because if you and something with itself, you get the thing that you anded. But this same exact syntax is used for the XOR instruction, the OR instruction, and it's an important one to cover. So we've talked about registers, we've gone over, a couple instructions. Next, to talk about further instructions, we need to go over something called the stack. And so what the stack is essentially is it's a region of contiguous memory that's used as kind of like a scratch space for functions and for various operations. So stack memory is used to pass data to and from locations. It's used for local variables, things like that. And we'll get into more advanced usage of the stack at a later date. But for now, what you need to understand about the stack is just kind of how it operates at its core level. So we're going to talk about two instructions that interact with the stack: push, which writes to it, and then pop, which reads from it. And we had those two registers before, RBP and RSP. So RBP points to the base of the stack, and then RSP kind of points to what we'll call the top of the stack. And since it actually grows from a high memory address to a low memory address, so talking about top and bottom with the stack is sometimes confusing. But just keep that in mind, and we'll have a graphic later to kind of go over how the stack works. But think of it as just kind of scratch space in memory that the computer can use to store values for later, because we only have so many general purpose registers. We need to be able to save things for later. And so that's kind of what the stack is for. And so we have these two instructions, push and pop, that interact with the stack. And so push will grow the stack by 8. And again, if this is still not quite clicking, we have an animation after this that might help this make sense. So push takes the value from the register that it's being called by. So this particular instruction will take the value in RAX and push that onto the stack and increase the stack pointer by 8 to point to the next location. And pop does the exact opposite. So it grabs the value that RSP is pointing to. So it grabs the value at the top of the stack and then decrements the stack pointer to then point at the next one. And so you can think of it as, you're stacking up plates, and then you're pulling plates from the same stack. So to sort of illustrate this, we have a PowerPoint animation here. So let's say we have this sequence of instructions. We're going to push RAX, RBX, and RCX onto the stack, and then we're going to pop the value from the stack off into RAX. So here's what that looks like with a nice animation here. So the first instruction executes, and we push RAX onto the stack. The second instruction executes, and we push RBX onto the stack. The third instruction executes, and you can guess what happens here. It pushes RCX onto the stack. But now when we run this pop RAX command, what that's going to do is pop whatever's at the top of the stack and store that in RAX. So this is going to be what the stack looks like at the end of this sequence of instructions. And so the stack is important for understanding how functions are called later, and it's often used to store local variables and things like that. But we'll get into that later on in the course and kind of how to interpret that. Right now, I just want you to be familiar with the concept of how a stack works and the instructions that manipulate it. And so next we have the jump and call instructions. The jump instruction just modifies the value in EIP or RIP, the instruction pointer. So again, what this does is it causes the code to jump to another location. And then call is used to implement function calls. And what that will do is it'll fix up the stack appropriately and then jump to a new location. And it does that so that when it's done calling that function, it knows where to jump back to. But we'll get into that in greater detail later on. What I want you to be familiar with now and kind of understand now is that call is used to implement function calls. And you'll see some of that with the exercises we're going to do. The last instruction we're going to talk about is compare, because you're going to see it a lot when it comes to things like control flow. So compare performs a comparison operation by subtracting the operands that is provided, except for there's no storage phase. So the result is never stored. And based on the result of this subtraction operation, if there was maybe an overflow, or if a signed bit was set, etc., flags in that R flags register are going to be set. And those R flags bits, the bits in that register, are important because the jump instruction has variants that will check those flags before actually performing the jump. So if the 0 flag gets set, let's say RAX contains 0 and the 0 flag gets set because we subtracted 5 from that, sets a 0 flag. Now the jump 0 instruction is gonna run. And if that flag isn't set, the jump 0 instruction won't jump. It won't modify EIP. And so that kind of gets into the topic of control flow and how programs determine kind of the map of which they're going to execute through. And we're going to talk about that a lot in the second session. But for today, I just wanted you to be aware of this compare instruction, kind of how it works at a lower level. And then lastly, what we're going to talk about with x86 64-bit today is addressing modes. We talked about this before, but essentially there's different ways instructions can reference registers in memory. So the simplest form is using an immediate addressing mode like this, where this instruction add RAX 14, right, adds 14 to RAX and stores it back into RAX. And you can also, as we showed before, you can do this on a register-to-register basis. So you can XOR RAX with itself, which again would kind of clear the value. But most importantly, what I want to show here is that you'll see things with brackets, which reference what's called, an indirect access. And this essentially treats these values like pointers. And that's something you're going to see fairly regularly. So I wanted you to be familiar with it. So when you see something in brackets like that, depending on the instruction, it's actually referencing what is at that memory location. And you'll see oftentimes, arithmetic operands get applied inside of these brackets. And so we have an example of that here and what that might look like with the Intel syntax. So to kind of wrap up x86-64 instructions, we're going to walk through, a very simple sequence of instructions here to make sure that we all are kind of on the same page. So this first instruction is going to move the value RAX or 2FFF into RAX. And you'll see we have our real-time PowerPoint debugger here that's going to kind of, highlight what's going on as we go through this assembly code. And so the second instruction, as you might have guessed, is going to move the value, hex 3000 into RBX. Now we're going to OR those two values and store the result into RAX. So you see that resulted in 3FFF in RAX. Now we're going to move hex 10,000 into RCX. We're going to subtract RAX from RCX, and we're going to then store the result back into RCX because that's our first operand. And so now we can see the result here. We went from hex 10,000 because we subtract 3FFF to C001. Now we're going to add RCX and RBX together. And where are we going to store the result? We're going to store it back into RCX. And so now we have a comparison instruction. So we're going to compare the values RBX and RAX. And you'll notice underneath of it, we have this JG, which is the jump instruction, but it only jumps if the greater than flag has been set. So we're going to compare these two values. And because RAX is indeed greater than RBX, are we going to jump to the greater than label and execute these instructions, or are we going to execute move RAX to? So let's find out. Let's dig through this. So the comparison instruction runs, and then it sets the appropriate flags, and now jump greater than runs. And because the value in RAX is greater than, we jump to this label. And so RIP now points to greater than as to the address that this would be at, as opposed to this other instruction. So then we move 1 into RAX, and then we return. And so that was kind of a lightning fast introduction to x86-64 and how the architecture works. I wanted to go through that because I wasn't sure, where everybody was going to be in terms of the architecture. We put resources up on the course page for those of you that might not be familiar with x86-64 and assembly language, things like that. And as we use Ghidra, you're going to find that it actually has a extremely powerful decompiler, which is implemented by understanding, the underlying assembly code. But it's still important for us to have that kind of strong fundamental core of understanding what's going on under the hood, because there are going to be times maybe when the decompiler doesn't work, or you need to go in and understand the assembly. So it's important to have an understanding of that. And I see that we have some Q&A here. What I'd like to do is get through the next section, because we are running not short on time, but we're going to be kind of cutting it close here. So what I would like to do is get through to the Ghidra section. So now that we've gone over what happens with how x86-64 works and things like that, let's talk about Ghidra and what we're going to use it for. So Ghidra is an open source software reverse engineering tool that was developed by NSA. It was open sourced in March of last year. It's Java based, and again, it's free, it's open source, which makes it kind of a big competitor in the RE tool market. There's lots of great reverse engineering tools that exist. We're mainly focusing on Ghidra because of all of the capabilities that it has and the fact that it's open source. And so Ghidra provides both a disassembler and a decompiler. We talked about disassembly before, and that's the process of going from those bytecodes back to assembly language. But Ghidra can take that a step further and actually go from that assembly language, or what it actually represents in terms of P code, into like a pseudo C code, and we'll take a look at that here in a minute. And so, it's actively developed. There's been lots of great community contributions to it since it's released. And in case anyone hasn't installed it and followed the instructions on the page, we have a slide here for how to, install Ghidra. But I believe most of you probably already followed the instructions that are on the page. If you haven't, here's the instructions for how to do it, manually. It's fairly straightforward to install. All you need to do is install, make sure you have Java 11. That's the one they recommend. And based on whether you're on, OS X or Windows or Linux, you run one of the two launch scripts, and then you can launch Ghidra. But, let's get into what you're going to do once it's launched. So Ghidra groups binaries into things called projects. So maybe you're looking at a game and you want to, keep it all organized. Projects can be shared, and there's also an idea of version control with projects, which is very cool. So if you're reversing something with a friend or colleague, you can commit a change to the project, and then they can pull it later. So you get like a nice collaborative reverse engineering environment going. And so, programs and binaries can be imported into a project. And so to create a project in Ghidra, what you're going to do is click on File and then New Project. And for the purposes of this course, you'll be doing a non-shared project. A shared project is one that requires you to run, Ghidra server, and you can then, add collaborators and things like that. But for the purposes of this course, you can just name this project HackadayU-Ghidra or whatever you want to name it, really. And so what's going to happen is you're going to be granted with this window. And so you select a location for the project and then, add a project name. It's going to ask you, do you want a shared or non-shared project? Again, for our purposes, you can just select non-shared. And you're going to be given this window. So this is kind of like the project management view. And so this is the HackadayU project. But now what we want to do is take this and load a binary. So we want to import a binary into Ghidra. And so in order to do this, you can go to File and then Import. And what Ghidra is going to do for you is it's going to go through and try to auto-detect the file format. So in our case, that's extremely useful because ELF is a well-defined, well-understood file format. And so the import window will pop up, and we'll go through this both in an exercise here in a moment and in animations in the slides. But Ghidra is going to, attempt to auto-detect the information that it can from the executable that you're trying to load, and determine everything that it can based on the fields in that file. So what that looks like is you'll select a file. So example, maybe you're going to load the CrackMe1 from the Git repo. You're going to import it, and Ghidra can already say like, oh, this is an ELF file. It was compiled for 64-bit. Looks like it was compiled with GCC. And so then you click OK, and you'll be greeted with, the result of importing the file. And so there's basically here it's talking about some information that it, read from the ELF file, etc. And now like this file has been imported into Ghidra, and you'll see this in the project view. And so now if you want to load the code browser and analyze it, you will double click on that program, and then you'll see like a green dragon pop up, and it'll open the code browser window. And so Ghidra can attempt to auto-analyze the binary, which again, information from the ELF file tells it, oh, hey, this address, this is where the program starts. And so Ghidra will go through and try to disassemble everything automatically, create and label any functions it might find, things like that. And so when you double click on the program, you're going to be greeted with this. And so this is kind of the code browser window. This is where you're going to be spending a lot of your time. And you're going to get a window that says, hey, this hasn't been analyzed. Would you like to analyze it now? So you're going to click yes, unless you don't want to reverse engineer it, and then you can click no, I suppose. And it's going to bring up, a bunch of analysis options here. So there are things to try to aggressively find instructions. There's, I know someone talked about finding like embedded or encrypted data. There's plugins to do that here. And so once you click analyze, Ghidra is going to go through, and it's going to take the bytecode that it sees and try to disassemble that and generate, assembly instructions from that. And then in addition to that, it also generates its intermediate representation that's known as P code, and it uses that to generate decompiler output. But we'll talk about that, later on. So, once you've clicked analyze and it's running, it's doing its thing, you get like the main program window open, and now you can start to explore and dig around. And these slides are kind of meant to be a reference for you later on, so that when you're looking at the exercises in Ghidra, you can kind of be aware of what's available to you. And so you've got the program tree that shows the segments that it found from the ELF file, the symbol tree, which grabs some of the symbols that it may have found, things like the data type manager, which show, the different types of the actual different, data types used during analysis, the listing, which is going to show the assembly code, and then you have the console for, tool output and things like that. So this is what the program tree looks like. Again, you'll see we have segments from the ELF file that are loaded in here, the symbol tree, which is kind of be our starting point. Every time we look at a binary in this class, you're going to look at the symbol tree and click on main to navigate to the main function, or the main entry point of the binary. The data type manager, if you have, a custom data type that you need to implement things like that, this is where you would do that. We're not going to do that maybe until lesson 4, but it's, it's a window that's useful when you need to use it. And then this is, the listing view. This is the disassembly view that you're going to spend a lot of time. And so this disassembly view is where, the resulting assembly code that's been generated can be displayed. And you can actually edit the way this looks by clicking on this symbol here and change what's displayed in the listing. And so we have an example of that here. So here's our main function that we've jumped to. And we have the address, or the virtual address that this instruction is at. Again, this is grabbed from the ELF file. The raw byte that represents this instruction. So this is the machine code, right? This is the raw byte. We have then the instruction mnemonic here, or maybe the opcode, and then the register that it's operating on. And so this is kind of the core piece of the listing view and the disassembly view. And then you also see something called XREFs, and what that stands for is a cross-reference. So this is Ghidra detecting, oh, hey, something else has referenced this memory location, because it understands enough of the syntax to generate these cross-references when memory locations are used or referenced. And so the next thing, the most powerful feature within Ghidra that we'll learn how to use is the decompiler. And so if the assembly code was kind of uncomfortable for you to read, it made you slightly uncomfortable, Ghidra actually has a decompiler that can take that assembly code and generate, pseudo C code from that. And so it's not, just to be clear, and for the pedants out there, the C code is actually generated from P code, which is Ghidra's intermediate representation of the instruction set. And we can get into that later, or in office hours, if people have more questions about it. But essentially, the decompiler is able to generate C code from the analysis that Ghidra has done. And so if we have this assembly code, which might look cumbersome to some of you, maybe you haven't worked with something like this before, it certainly doesn't look fun to read. The decompiler will take that and give you this, which, if you're a reverse engineer, this is extremely powerful, because now you've gone from looking at assembly code to, decompiled code. And this is kind of the core sort of selling point of Ghidra. And we're going to learn how to approach a binary from both angles. We're going to look at assembly, we're going to look at decompiled output, and we're going to kind of make sure that we have an understanding of how to use both, because you don't want to always rely on the decompiler, but it is extremely powerful, as you can see here. So Ghidra also has a byte view. So if you want to see, the raw bytes that are generated outside of the assembly listing, you can do that. And you can also, synchronize it so that they line up. And when you highlight an instruction here, you'll see that it jumps over here. And there's a handful of other views. I mean, there's lots. We'll get into more of the views, later on in the course. But you have the defined strings that it finds. You have, defined data types that it found, things like that. And there, you see there's some strings in there from the decompilation example that we were looking at. And you've got the function call tree, which is pretty interesting. So this shows, okay, from main, I call, strtl and puts. And so it's kind of cool to be able to see, what functions are called from your main function. And so all of these are, available to you, in Ghidra. But, how do you navigate once you're in there, once you're in the listing view? So you can scroll through the listing view. You can use the arrow keys. It's fairly intuitive with how you navigate. And then when you're looking at those XREFs that we talked about earlier, you can double click on that and it'll jump to the location that's referencing it. And you can also jump to a particular location in memory by pressing the G key. And so with all that, we've generated, challenge binaries for this course. And each of these was kind of developed to kind of highlight the Ghidra features that we talk about, as well as the x86-64 features that we're going to talk about, because as the exercises get more complex, so are the challenges. And we're going to review these during office hours. The page is up and active, and we'll respond as best we can to people's queries on the page. And then I think the plan is probably on Wednesday to release maybe an advanced challenge for those that are maybe ahead of the course. And so we have about 5 minutes left on the timer here. And so what I'd like to do is walk you through how to load exercise C1 in Ghidra and how you might navigate that. So let's go ahead and do that. So if you haven't downloaded the exercises, go ahead and do that from GitHub. The link is there. It's also up on the page. This repository is going to hold all the materials for the course, and the plan is, before session 2, we're going to upload it with the exercises from session 2, same for 3 and 4, and you'll be able to pull that down whenever you want. And also, if you have, things you would like to see in it, I'm not opposed to pull requests and things like that. But so let's get out of PowerPoint and let's load this binary into Ghidra and see what it's doing. So I have a Ghidra project here, and what I'm going to do is, so we can start from square one, we have our Ghidra project. Mine's called Hackaday. I'm going to go File, Import File, and then I have the exercises here that I pulled from the repo. And so let's load up C1, Challenge 1. We can see here that Ghidra has already figured out, the format. It's telling us, oh, it's 64-bit, x86, looks like it was compiled with GCC, and they are 100% correct. And so you can name it something different if you want it to look something different in the program view. So we'll just call it Challenge 1. And then again, here's the results of it being imported. And now that we're here, we can double click on this, or we can click here. Of course, it loads halfway on the other monitor. And so it asked me if I wanted to analyze. I clicked yes, and then I clicked analyze. So here we are. We're in this listing view. The first thing you want to do with these challenges is go to the functions tab here in the symbol tree. So this is going to tell us, the imports, the exports, the functions that it's able to find, and we're going to jump straight to main, because if you've written C code, you understand that, main is the entry point for, an executable as defined by the EABI. And so before looking at any of this, because this gives it away, we can look at the assembly here, and you'll see that we have, it's setting up this, we're setting up the stack here, and this is setting up the environment variables, or the variables that are maybe passed into the C program, setting these up as local variables on the stack. But we're going to get into doing kind of more, detailed analysis of these during the office hours, and we're going to kind of walk through exactly how these work. But from an extremely high level, if you were to look at just this assembly for a second, you can see that it's grabbing a string here. It's loading the address. LEA is load effective address. It's loading the address of what looks like this string. So if we double click this, we jump down here to a string that says, please supply the password. Okay, well, we go back to where we came from by clicking the xref from that, and then we call the puts function. And so even without, a detailed understanding of how function calls are implemented, you can probably assume that what this is going to do is print out, please supply the password via the puts function. And again, if you're looking over here, you can see that that's exactly what it's going to do. So we then, the puts call occurs, and then here we've got a call to, string length, and it looks like it's just calling it with the string HackadayU. And so we can look at this memory address and see what's there. We have this string HackadayU, And we can see here in these xrefs that it's actually referenced multiple times throughout this program. And so let's jump back to the main function where we came from. So it's grabbing, presumably we're grabbing the length of this string here, right? So even without knowing, the EABI, which we're going to get into in the next lesson and during the office hours, we can assume we're calling string length here on the HackadayU string. And again, if you're looking at the decompiler output, you can see that that's true. And so next you can see that we're grabbing some variable here and we're storing it in RAX. And then we're dereferencing that variable with another move instruction and storing that back into RAX. And then we're storing into RSI another variable here and calling string compare. So what we're seeing here is that we're taking this HackadayU string and we're comparing it with some other string, right? And we'll get into in more detail how we can tell what the string is during the office hour, but it's a pretty safe assumption that this string that's being compared against it, right, is our password string. And so after this is called, so we call string compare on both the HackadayU string and then whatever's in this local variable here, we check the return code for the call instruction because the return code is stored in EAX for this instruction. And then depending on whether it's 0 or not, we jump to either printing, we can see here if we look in the decompiler output, correct or wrong answer. And so it's fairly straightforward. If you sit down, with the Intel manual, you can go through and figure out exactly what each of these instructions is doing. And it's important to do that. So that's something you want to do before the office hours if you can, or just before the session next week. And we'll be available on the course page to talk with you about it and things like that. But looking over at the decompiler view, it's pretty clear what this program is doing, right? So if you provide a password, it does a string compare on it, and then if that string compare, if it's equal to HackadayU, we print correct, otherwise we print wrong answer. And so the purpose of this was, and we can verify that, right? So if we run that program, and those of you that were paying attention probably saw that I had the answers up already, but if we run that program with no arguments, it says, please supply the password. All right, well, let's compare that with our decompiler output here. So we're checking whatever this parameter is, whatever this is, and if it's equal to 2, we execute this block of code. And you can see that when we highlight the bracket here, it shows us the closing bracket. So if taking what you might know about C code, it could be checking any number of things, but there's a good chance that it's checking, argc, or the argument count. So let's find out. If we just do C1 testing. Okay, we're saying wrong answer. We'd never use, and then you see we have the format string %s followed by this local variable. So this local variable is our password, right? So this parameter 2 plus 8 is pointing to our password, and that is indeed what's getting passed to the string compare that's comparing it with HackadayU. So let's see what happens when we run C1 HackadayU. I think everybody can probably guess what's going to happen here. And it says correct, the password was HackadayU the whole time. And so I know we're about out of time here. So exercise C2, if people want to load that up and take a look at it, I'll be available to talk about it. There's the chat room on the course page, and we can kind of go over that if people want. And run this application, see what it's doing differently, and see what it's doing, and figure out if you can determine what kind of password it might be looking for. And so to finally wrap things all up today, what we covered was quite a bit. So I apologize if we went over a little bit here, but we covered, the basic x86 instructions. We covered how software is built from an extremely high level. We went over, some common Ghidra features, and then we talked about how to navigate and use Ghidra. And the office hours are going to be more of what we just did, of us loading up Ghidra together and walking through these exercises and getting more of, that hands-on experience. And so were the rest of the lectures. This one was definitely the most, text and kind of the most info. So my apologies if it felt like a fire hose of information. There was just a lot of ground to cover to make sure everybody was on the same page. And if you have any questions about what we talked about, feel free to message me on the page. Um, no stupid questions here. Everybody's coming from different backgrounds, so whatever questions you may have, let them rip, and we'll do what we can to fill those gaps.